All right, well, good afternoon, everyone. My name is Yuval from EcoWave Power. I'm at EcoWave Power's R&D Manager, and I'll be talking today about our wave energy pilot, which is looking at advancing wave energy with real-time data and forecasting. I'll start with a bit of a project overview and the objective. So we're looking to support wave energy commercialization by providing accurate nearshore wave energy data for assessing locations for future wave energy converters worldwide. There are current challenges in installing new wave energy converters, which is that wave energy potential is often estimated using mid-ocean data, which comes from satellites, and on-site measurements are required for accurate wave energy forecasting. And what we're looking is to bridge that gap. So in our pilot project, we're testing 5 types of sensors to measure wave data, and then comparing that sensor data with mid-ocean data to assess accuracy and forecast future sites' energy potential. The impact of this, or what this really means, is that it helps secure debt financing for wave energy projects, as well as optimizes energy forecasting and maintenance processes. There's also a broader benefit, which is helping businesses, research institutions, and universities gain more accurate wave energy assessments and supports better site selection, wave energy station design, and innovation. I'll just go give you guys a bit of a crash course into wave theory. So what happens is that waves in the ocean have typically a very consistent wavelength, which is independent to the surface or of different bodies. But as the waves approach the shoreline, they change, which by interacting with different structures and the shoreline. So what that means is that the waves end up breaking, which is great for surfing, and generating energy from the waves. It also increases in the wave heights. The waves refract around objects, and there's also rip currents, which need to be taken into account. For our wave energy pilot, we used our pilot station in Tel Aviv, Jaffa, which is in Israel. This is a 100 kilowatt station, which uses our technology of point absorbers with a hydraulic system. And the site is in operation today, sending electricity to Israel's national electricity grid. I'll give you guys a brief overview of the data acquisition. So what we've done is we've been looking at, we started by looking at analyzing various types of sensors, and we were looking for accurate wave data for nearshore applications that are simple to install and cheap. And this table below shows the sensors and the types of technology. So firstly, we have, well, the satellite data, which is mid-ocean data. Typical resolution for this is hourly, which is a disadvantage, but the advantage is that satellite data and mid-ocean data there's many years of historic data for many locations. On the other hand, for the sensors, we looked at radar, ultrasonic sensor, gyroscope, a wave buoy, and the Taltech hydrostatic pressure transducer. The advantage of this is that you get very high resolution of 5 Hertz, which is 5 times a second. But then the disadvantage is installing these must be installed at specific sites. And as mentioned before, we're looking to bridge this gap so that we could forecast energy generation from sites simply by taking mid-ocean data and then and validating that through on-site sensor assessments. A bit more into data acquisition. So satellite data, like I mentioned, it's available for many locations around the globe, and it does this by usage of wind and wave data, as well as topography to produce wave hindcasts and nearshore wave studies. The sensors deployed are displayed here on the screen. We had the water level radar from Vega. We used an ultrasonic sensor from Obscape. We installed a gyroscope onto one of our floater arms. We tested a wave buoy and the Taltech pressure transducer. What we found is that the first 3 are sensors which are installed above the waterline, and the wave buoys are on the surface of the water, and the hydromass sensor is underwater. And what we found is where we look for gathering wave data is quite harsh conditions where the waves are breaking and it's quite turbulent. And what we found that the sensors which work best are the ones which are installed above the water, secured away from the very large wave forces. So we're gathering data for the first three, and the two, the wave buoy and the transducer, were found not able to survive the conditions at our particular site. Here's a photo side view from our wave energy station. We can see the radar and ultrasonic sensor, which were installed on a mast about 6 meters above the floaters. They're pointing towards the water. It looks like they're on the floaters, but that's just because of the picture. And there's also the gyroscope, which is installed onto the floater arm. Here's a comparison for looking at the satellite nearshore data versus the ultrasonic sensor. The light blue is the radar, and the dark blue is the mid-ocean results from for the significant wave heights. There's the top graph is for the wave heights, and the bottom one is for the period. And what we found is that satellite data closely matches the ultrasonic sensor readings for the significant wave heights, but does not align well for the wave periods. We also looked at historic data because there is a correlation between waves between year to year. So looked at wave hindcast for satellite, and we compared that to the ultrasonic sensor of 2024. And what we found is that when you're looking at the average significant wave height, you get very similar results, which is good to see. But then we saw that the ultrasonic sensor gives higher readings than the satellite results, to show that there's potentially more energy available at specific locations that might be measured, or that might be provided from the metocean data. We also conducting experiments on the radar versus ultrasonic sensors. Here's a sample of a day and a half, which was taken quite recently when we had a starting of a storm in Israel. And as you can see, the ultrasonic sensor reads higher for wave heights above 1 meter waves. What we can see is that the ultrasonic sensor, the obscape sensor, is fluctuates quite a lot, while the radar seems to be better technology for measuring waves where they are breaking. Here's a picture showing a picture of the station during a storm. You can see there's quite a lot of turbulence there and very large wave forces. And we believe that the wave breaking below the sensor leads to a discrepancy between the radar and the ultrasonic sensors. And we believe that the ultrasonic sensor is recording the splashes from the breaking waves, which adversely impacts the sensor readings, which is a very good finding because the variability between the heights changes the amount of energy that is recorded in sites. Go through a bit of conclusions and the next steps. So the conclusions is that in the wave breaking zone, sensors installed above the waterline survive the harsh conditions. Also, it appears that satellite data underestimate the wave energy, and radar measurements offer more consistent wave data than the ultrasonic sensor, particularly for breaking waves greater than 1 meter. So what are the next steps? We're very excited that we're approaching the wavy season here in Israel, which is set to begin in December, and all our sensors are deployed and ready to go to measure the very large waves that we're expecting to see. So we'll be collecting data from the ultrasonic, the radar, and the gyroscope sensors, and then this data will be compared to the satellite-based mid-ocean nearshore information to determine which sensors provide the most accurate information, and determine the strength of correlation between the nearshore mid-ocean data and the on-site sensor readings. And then we'll be able to take that data and then have a better resolution we'll be able to provide better resolution in determining sites for future wave energy stations, as well as this data would be interesting for marinas, jetties, and other businesses which operate near the shoreline, which are impacted by waves. That's the end of my presentation. Are there any questions?